So now I want to talk about the types of atoms, the octet rule, and the periodic table. So let's start here with the types of atoms. So I've color-coded, and this isn't very, I don't have any symbols on here because I don't want this to be too cluttered. This might get cluttered pretty quick. So let's look at the types of atoms here. These pink guys here are the alkali metals. Now these are very reactive. If you put them in water, they'll likely explode, or they'll likely cause some sort of flame or something like that, and we'll see why in just a few minutes here. Okay, so the properties of these guys are that of these alkali metals is that they're very reactive in water and very reactive in general. Now these guys here are the alkali earth metals. And together, these guys form the true metals of the periodic table. Okay. So these are the true metals of the periodic table. These guys here, these are the transition metals. Now these transition metals have interesting properties to them. In biochemistry, they're very good at transporting electrons across different protein domains, and we see many of these in the electron transport chain in biochemistry that follows the Krebs cycle, and we'll touch upon that in a biochemistry playlist. We'll also see transition metals acting as very good semiconductors, okay, because they're still relatively stable when their electrons get excited into different energy levels. They also make good piezoelectric materials. Those are materials that when they're warped or stretched in a way, they still stay relatively stable, but they exhibit properties that transition from one to the other that are interesting for us and useful for us to understand and study. These here are the metalloids. These are the metalloids. Okay. These again have interesting transition properties to them. They're the sort of the transition between the metals, the metals, and what these guys, which are the non-metals. Okay. Then we have these guys, which are the halogens. And halogens are very reactive, and we'll see why. These guys are the noble gases. Noble gases. The noble gases are not reactive at all, although they react in some rare circumstances. These here are the unknowns, and many of them are becoming known now. Okay, but their property is that oftentimes they're very unstable. Their lifetime is on the span of seconds or nanoseconds. So these guys are not very stable. These guys are the lanthanides. And these guys are the actinides. The lanthanides and actinides, they are the foundation of nuclear chemistry. Many of them are very unstable and will sort of degenerate into more stable elements. Okay. We have this is where uranium lives. This is again this chemistry here is nuclear chemistry. Okay, and we'll go over that as well in another playlist. All right, now let's talk about some of the periodic trends. So let's start with the concept of atomic radius. So here we have hydrogen. Hydrogen looks like this. It's got one proton in the middle, and it's got an orbiting electron. Okay, one orbiting electron. Here we have helium. helium has 2 protons in the middle and 2 orbiting electrons. These are electronically stable atoms. They look like they have this configuration to them. And here we have lithium. And what happens is we now have 3 protons. Our inner shell is filled, and all the shells after that can take on 8 electrons, and that's the octet rule. Okay, so here we have 1, and then here's beryllium, and beryllium will have a second electron in its outer shell. Boron here will have a third one, and then 4th, 5th, 6th, 7th, and so on, until we have 8 total, because we have 1, 2, 3, 4, 5, 6, 7, 8. We filled our shell, then we add another shell to this atom here. Okay, we go across the periodic table, and we have another shell here, another shell, and now once we hit the transition metals, then the octet rule doesn't really work that much, okay? But in general chemistry, you will be expected to know the octet rule works for all of these guys in group 1, okay? Group 2 is this column, group 3, and then group 4, group 5, group 6, group 7, okay? And these guys will fit right in here. Okay? So these are groups. Okay, group 1, this is group 2, okay, and group 3, and so on. The rows here are periods, okay? So this would be period 1, period 2, period 3, period 4, and so on, okay? Now let's talk about the periodic trend. So we talked about the octet rule. The octet rule is we want 8 electrons. No matter if it's electronically stable or not, many of these want 8 electrons in their outermost shell, okay? So you can imagine for lithium, if we take away an electron, its outermost shell is filled. That's a more general form of the octet rule. We want the outermost shell to be filled, okay? And it will be happy. Many teachers say this will be happy once its outermost shell is filled, and it becomes ever more harder to take away an electron as we go across the periodic table, okay? And that's roughly akin to saying that the ionization energy, so the energy required to take an electron away, increases as we go across the periodic table. So the ionization energy increases, okay, going this way from right, or from left to right. Okay, so ionization energy increases. Ionization energy will also increase as we go from bottom to top, okay? And that is because, again, we're talking about energy, the energy required to take away an electron. Down here, it's really, really easy to take away an electron away because the electrons are so far from the protons that they don't feel any effective charge or any effective pull between the protons and the electrons, those outermost electrons. And again, we're talking about the outermost electrons in the context of energy. How much energy do we need to take an electron away from the atom? And here, therefore, it's easier, or it becomes harder, it becomes harder to take an electron away as we go from bottom to top. So the ionization energy increases. Going up. Okay, So the ionization energy increases. Likewise, this, so now we want to talk about the affinity of the electron, not the energy for us, not the energy. We want to talk about the affinity. The affinity of, or the ability of the atom to gain an electron. Now you can see here, the ability is going to increase as we go from left to right here, because these guys, all they need is one electron more to be stable, or to be happy, to be in that state of the octet state. Right? So all they need, so it's really, really easy for them to gain an electron. So the electron affinity, increases going this way as well. And we can see also here that the electron affinity will increase as we go from bottom to top here. Because these guys up here will have a stronger pull on their outermost shell, and so electrons anywhere from around them will be pulled in closer, okay, because the radius, the outermost electrons are shielded less. That's another concept that you should know, is shielding. They're shielded less as you go up the periodic table, because we have less and less shells surrounding that nucleus. Okay? So those are the two big ones, ionization energy, electron affinity, and then obviously we have the atomic radius. The atomic radius goes in the opposite direction. The atomic radius increases as we go down this way. So that's the radius. Goes down this way because we're adding shells, and it decreases going this way, so it increases as we go this way. So atomic radius increases as we go this way. And the reason for that is because we're adding more and more protons as we go from right to left here. And as we add more and more protons, the overall charge of the nucleus becomes stronger and stronger and stronger as we are going across from left to right. Okay? So that means the radius decreases as we're going from left to right, so it increases as we're going from right to left. All right, so we could say that the ionization energy increases as we go this way, and the electron affinity energy increases as we go this way. And electron affinity increases as we go this way. We're just following the overall trend of these two arrows that we made, and oppositely, the atomic radius increases as we go that way. So we can have some practice problems now. We can say this atom here has a larger radius than this atom here, okay, because the trend is this way. Or this atom here has, this atom here has a smaller radius than this one here. Larger, sorry, I'm getting a little bit confused here myself. So it has a larger radius than this one here because the radius increases as we go this way. So as this guy here has a larger radius than this guy. Clearing that up. This guy here will have a higher ionization energy than this guy here. Okay, because this guy here is further away this way than he is up. Okay? And so we can begin to make sense of the ionization energy, the electron affinity, and the radius, the groups, the periods, the different types of atoms, and we've covered everything. I know this video has gone a little bit over by 5 minutes of what my usual time is. However, this covers a lot, and this will allow us to get even closer to some of the calculations that we'll be able to do in chemistry, and some of the more interesting things. So I'm really getting a lot of this preliminary stuff out of the way so that we can really get to the nuts and bolts of chemistry and really be able to do some calculations and understand what's going on. If you like the way that I teach, please go ahead to my website at tristancarmacy.com. Go ahead and hit that subscribe button if you want to, if you like this kind of content. Again, I just recently started a tensor calculus playlist, and I'm going to be starting other playlists as well. I wish to see you in the next one, and have a good one.